Okay, this is the second in our series of lectures providing a basic introduction to solution of a system of linear equations. In this one, we're going to look at the nature of the solution, the uniqueness, whether we can get a solution from a somewhat theoretical point of view. We're going to start from our basic example of beverages, where we had some number of beers, some number of wines, and we knew the total number of beverages sold was 150, and we had some. The beverages are $5 per beer and $8.50 per glass of wine, and we know we had made $855 at the end of the night. The question is, what is B and what is W? Now, if you're given this, again, this simple problem, you would be able to solve it algebraically by just solving for one unknown in terms of the other, plugging into the other equation, solving for an equation and one unknown, solving for that, and coming back, solving for the other. But again, scaling kills that process. Once you get to very large number of unknowns, even 10 would get tedious, let alone 10 million. So we're able to write this in this general way, ax equals b, which could represent a system of two linear equations or a system of 20 million linear equations. The question is, when do we get solutions of this, and what does it mean about a, b, x, so we can set up our problems properly. If we come back to these two things here, we also see we can think of this as an equation for a line. For example, if we have b equals minus w plus 150, we see this as equation for line, somewhere in the form y equals mx plus b, where b is equal to, getting confused here, well, there's a different b. Your intercept here is equal to 150, and your slope m is equal to minus 1. So if we were to draw this using a simple set of axes, we can draw both these equations as two equations and two unknowns. So here we're at, these are all positive numbers, here we are at 0, 0, so we'll draw b on this axis, we'll draw w on this axis, and if we start here at, excuse me, at w equal 150, we have this equation that we have our slope equals minus 1, slope is minus 1, and we have our other equation, which is going to start somewhere around here. It has a lesser slope. If we come back here, we can also write this equation for b in terms of, should be w here, w, right? So divide this by 5 and bring that w over to the other side. We have a second equation for b as a function of w, or we can write as w as a function of b. Doesn't really matter. And we have two equations for two lines. And we see that those, we're searching for the values b and w, and those occur when both equations are satisfied. The only times both relationships between b and w are satisfied is when these equations intersect, which occurs right here and happens to be for this set of equations at the point where b equals 120 and w is equal to 30. I think that's correct. So 120 beers and 30 glasses of wine. If we go back and plug those into these equations here, they should satisfy, these equations here, it should satisfy these both exactly. So we know we have the correct solution. So again, these equations represent, in 2D, represent lines. We can write w as a function of b, just like y equals a function of x, plot it, and a w versus b. We have two lines. So along this blue line, I'll make this blue, along this blue line, the first equation, b plus w equals 150, is satisfied. Any combination, so you might have 150 glasses of wine and no beers, or maybe you have 150 beers and no wine, or maybe you have 75 of both. So that equation this blue line satisfies that first equation, combinations of beer and wine. The red line is the combinations of beer and wine that satisfy the second equation. There's only one point here that satisfies both equations, and that is in the intersection. That intersection represents the solution of the system of equations. So because they intersect, we know there's a solution. We can solve for it. We can solve for the intersection, and there it is. So that represents our problem as that. If I slightly augment our system of equations, let's say, the numbers came in, and or would say there was different information, and that information was that the cost of wine was actually $5. So let's say I have this system of equations. I knew my beer plus wine beverages was equal to 150, and I have my beer were $5, my wine was $5, and I brought in, say, $750 over the night. If I plot these two functions, I find the following, that the solution of this is a line that looks something like this, where I have my 0 here, I have a 0, so this is 0 to 300, and this is minus 150 to around 150. And my second equation, if I were to plot it, plots directly on top of it. Right? If you notice here, this second equation is the first equation multiplied by 5. So if I take this first equation, I multiply by 5, I get 5b plus 5w, and 5 times 150 is 750. So essentially what happened here is two things. Graphically, we see how many solutions are there, how many points in BW space are there that satisfy both equations. Well, the answer is there's an infinite number. This point, this point, this point, this point, this point. There's an infinite number. And we see also, why is this? We now have an infinite number of solutions. What is the issue? The issue, as we can see right here, is that the second equation did not bring any new information in. Remember, I have two unknowns. I need two equations to satisfy those two unknowns. If I only had the first equation here, this wouldn't be enough, right? I know some combination of B and W that will satisfy it. I can always tell you the combination, or I can tell you one is a function of the other, but I cannot get unique values for either of them. It's not possible. So I bring in a second equation. Normally that will provide the unique values, but here the second equation doesn't provide any new information. So I have an infinite number of solutions, and that's graphically we see that these two lines are coincident and intersect at every single point. I'm going to bring in one more scenario. I'm just going to change the amount of dollars brought in at the end of the night. Everything else will be the same. I have B plus W equals 150, and I have 5B plus 5W is equal to 855. So I changed the price. Now you see that if I multiply this first equation times 5, I do not get the second equation. If I plot these two graphically, I won't go through the exact numbers. I will end up with two curves which have the exact same slope but are not coincident. They are parallel but not coincident. And so what I have here is no intersection and therefore no solution. If I come back here and solve for B as a function of W and plug it into here, I will find that I have basically an incompatible left and right side. There's no solution to this system of equations. There's no combination of B and W that will satisfy both of these systems of equations. So I have basically three possibilities. I have a solution, which we will not prove, but if we can show to be unique, a single unique solution. I have an infinite number of solutions, where essentially I cannot provide unique values for B and W, but I can give you B as a function of W, or W as a function of B, the relationship between them that satisfies those infinite solutions, and I have no solution. So there's three possibilities, and we ask ourselves, okay, fine. For the beer and wine example, it's pretty straightforward. But otherwise, what is going on here? How can we think about this when we get to if we have 10 million unknowns and these sort of things? What if we come back to our ax equals b? What is it about ax or b that's causing these problems, and how can we determine if we're going to face these similar problems when we get to a very large uh, system of equations? So what we're going to do is let's go back here and rewrite this problem. So you have a11, a12, a21, a22 times x2, x1, x2 equals b1, b2. So again, we wrote our age structure model in this form. We can write our beverage problem in this form, where we have these constant coefficients a. This is the unknown vector, x, and b is what we call our usually referred to as the right-hand side, RHS. This is our vector of unknowns. And again, this is a, our constant coefficient matrix. So this system looks something like this. So we have two equations, a11 x1 plus a12 x2 equals b1, and we have a21 x1 plus a22 x2 equals b2. I'm going to write this a slightly different way. I'm going to write this as a11, a21 as a vector, a column vector, times our unknown x1 plus a12, a22 x2 equals our column vector b1, b2. And we'll return to that in a second. Keep in mind what we have here. These two things are the column vectors of A. Compare them to this. It's this column vector ends up getting multiplying by x1. So x1 times the first column of A. This a12, a22 here is the second column vector of A. So the first column vector of A times x1 plus the second column vector of A times x2 equals b1, b2. Remember, x1 and x2 are the unknowns in this equation. And so really what we're writing this as is a some vector v1, or column vector, first column vector of A I'll write as v1 times x1, the unknown scalar, plus column vector of A v2 times x2, an unknown scalar, equals b. So I've sort of rewritten the equation into this form. Again, the x's are unknowns and they are scalars. And what this equation says is I'm going to add together two vectors, but they are scalar multiples of these vectors. I have x1, again a scalar of v1, plus x2 of v2 equals b. So I'm adding these two vectors together. Remember, a scalar times a vector is a vector. So I'm multiplying my first vector times some scalar plus the second vector times the scalar equals b. And these scalars are what I don't know. This is known as a linear combination. I'm making a linear combination of these two vectors, v1 and v2, and asking, can I find a linear combination? Can I find an x1 and x2 that will allow me to create this linear combination and make a vector b? Let's think of this in very simple terms. Let's say v1 was the vector 1, 0. And v2 was the vector 0, 1. And b were the vector 1, 1. So I have three vectors, 0, 1, 1, 0, and 1, 1. Now what happens when I multiply? Well, let's think in the simple case here. Could I add, this is vector 1 displayed graphically, vector 2 displayed graphically, and b. Can I find a linear combination of v1 and v2 that when summed together make a vector b? And remember, when we sum a vector, we can sum the components, or we can think of it as head to tail. So if we add directly, for example, v1 plus v2, I will get 1, 0 plus 0, 1, which is equal to 1, comma 1, which is equal to b. And I can see that graphically here. If I add v1 and if I add v2 to it, I'm going to move this over head to tail, I arrive at b. So my linear combination that produces a result is 1, let's not write it that way, is 1 times v1 plus 1 times v2 is equal to b. Now let's take a slightly more complicated example. Let's make up a b that looks like this. Here's my b, and it's equal to 3, comma 1. And my x1 is again this vector down here, 1, comma 0. And my y1 is this vector here, 0, comma 1. I'm sorry, my x, v2, v1, and b. Can I find some linear combination of v1 and v2 that will make a b? Well, let's plug in the answer and then we'll go back and look at it. The answer is 3 times v1 plus 1 times v2 is equal to b. Right? So we have 3 times v1, which is equal to 1, 0, plus 1 times v2, which is equal to 0, 1. Right? We multiply a scalar times a vector. Each of the elements get multiplied by that scalar. So it's equal to 3, 0 plus 0, 1, which is equal to 3, 1, which is equal to b. What did I do? I multiplied that first vector times 3, times 2, times 3, and now I'm here, and I add vector 2, and I get there. So there is some linear combination, 3 of v1s and 1 v2, I can use to build a b. So that's the question I'm asking. Again, going back to where we started, let me just scroll back. We wrote this system of equations like this. We want to know x1, x2. I rewrote it in a different form where I can write it as first column vector of A times unknown x1 plus second column vector of A times unknown x2 equals b1, b2. These are unknowns. Can I form a linear combination of the column vectors of A and make this right-hand side b? Then we started tinkering with simple vectors v1 and v2, and we were able to do it. Let's do a couple more with v1 and v2 to see if there are circumstances. I put some simple circumstances. What about some other circumstances we might have? What if this were v1 and this were v2? So I have here v1 is equal to 1, 0. And v2 we're out here at say 3, 0. And this were b equals 2, comma 2. So v1 is 1, 0, v2 is 3, 0, and b is 2, 2. Is there any combination of these vectors, v1 and v2, that will make a b? We multiply any scalar multiple of this vector v1, it will always lie along the x-axis. There's nothing I can multiply by this that will produce any y. That will always be 0. 0 times anything is 0. Same with v2. It is stuck in this x-axis. We can stretch and scale and move, make any vector we want on the x-axis, but we can never make a b because it has a non-zero y component. It's impossible to get out of that x-axis. So the answer is no. If we write this again as v1 x1 plus v2 x2 equals b, there is no x1 and x2 that will make, that will work. So there is no solution to this problem. There's no solution to this problem. However, if I slightly modify that problem, let's call this x1, and again, this was x2, right? Then let's just say b was not out there. B was in the x-axis. We'll just put it backwards right here. So I have 1, comma 0. I have 3, comma 0. And I have minus 1, comma 0 is my b. b, x1, x2. can I find, oh, I apologize, I switched to X. Let's go back here. This is V1 and V2. Can I find a linear combination x1 scalar times v1 plus x2 scalar times v2 that's equal to b? Is it possible to do this? So remember, x1 and x2 are unknown. I see one right now, which is that we have minus 1 v1 plus no v2s. This is equal to b. I can see right here, all I'm doing is taking this vector and just making it the negative, and I ignore v2 altogether. Or I could do, let's see, we could do no v1s and minus a third v2. So we flip v2 over and scale it by a third, and we could get a b. And we'll find out there's other combinations. We can have both v1 and v2. In fact, there are an infinite number of solutions for x1 and x2 that will result in getting a b. So there's an infinite number of solutions. So what is going on? Okay, so let's look at these two cases. One is, just to contrast them, let me draw them all together actually, just to contrast them. Just sketching what the vectors were looking like. We have three axes, and I'll draw my v1s and v2s as green vectors. The first case we had a v1 like this and a v2 like this, and a b was up the middle. The second one we had a v1 this way and a v2 the same direction in the same line. And in the third case we had the same scenario. We didn't change the vectors, the v1 vectors. I'm going to make b blue. In this case, this was b, b. In this case, we put b backwards. So those are the three cases, and to remind you, we had a unique solution for x1, x2. We had no solution. We had infinite solution. Thinking in terms of what's going on, remember, to get a unique solution, we have to be able to construct B using some linear combination of V1 and V2. Again, the fundamental problem is x1 V1 plus x2 V2 equals B1, equals B. So this is the fundamental problem. And again, this comes from AX equals B, where V1 and V2 are the column vectors of A. B is B. X is a vector containing the unknowns, scalars, x1, x2. So could we find a linear combination of vectors that makes a B? In this first case, we have these two vectors like this. Now these vectors are not parallel, and we can use these linear combination of vectors to make any vector in 2-space. I can produce any vector in 2-space using V1 and V2. We say that V1 and V2 are linearly independent. What that means is I can't make one from the other. I can't make a V2 from only a V1. And most importantly, maybe easier to understand, is that they span the space of 2. We're working in 2 dimensions. Our matrix is in 2 by 2. Our number of knowns is 2, and they span the space of 2. I can use those vectors to generate any vector in this entire space right here, because they're linearly independent and they span the space of 2. In this second case where I had a V1 this way and a V2 this way, the span of these two vectors is 1. I can only create, with these two linear combinations of these two vectors, I can only create stuff along this line. So the space they span is one-dimensional. They can't produce any this vector, this, they cannot produce any of these vectors. It's not possible because they are collinear in 2D, and when we get to higher dimensions, it's more difficult to think of, but it's the same concept, that The combinations of the vectors do not span the entire space. In a 3x3 matrix, they have to be able to span 3D. So if you have all three vectors being coplanar, then they can only form vectors within that plane and not within the full 3D space. In 4D, 5D, it's harder to talk about, but the concept is similar in terms of span and linearity, linear independence. So in that last, so this was the case of no solution for B unless, case 3, you have your V1 and your V2 collinear spanning this simple 1D space, and your B happened to lie in that space somewhere, right? If B happens to lie in your space, then you could get a solution. In fact, this was the infinite solution case. So it depended on the nature of B. So whether or not you have a unique solution or not depends on the nature of the column vectors of A. Do the column vectors of A span the space of A? Is A 2x2? Do they span 2 space? If A is 3x3, do they span 3 space? That tells you whether you have a unique solution if they do span it. If they don't, then you're not getting a unique solution. Then the question is whether it's infinite solution or no solution, and that depends on the relationship of B and the column vectors of A. If B lies in the span of the column vectors of A, meaning it's in 2D, it's collinear, then you get an infinite solution. Otherwise, you can't find any linear combination of the column vectors of A that will make B, and there's no solution. So those three scenarios are important, and they determine whether or not, when you have a very large system of equations, whether you're not going to get a solution, an infinite solution, etc. So there's a lot more detail about this, about rank and linear independence. I put a link to a PDF that goes into more detail about linear algebra on the web if you want to read more about that.